You are made of dead stars. Right now, sitting wherever you are, every single atom in your body, the iron in your blood, the calcium in your bones, the carbon in your DNA, was forged inside a star that exploded before our sun even existed. You are not on Earth. You are not from Earth. You are a piece of the universe that the universe bent back on itself and made aware. And in the next hour, we're going to trace exactly how that happened from the moment before time existed through 13.8 billion years of explosions and silence and darkness and fire, all the way to the second you pressed play on this video. Stay with me, because by the time this is over, you will never look at the night sky or your own hands or the air you are breathing the same way again. This is not a space documentary. This is your origin story. Before we dive in, if this kind of content speaks to you, subscribe right now because we do this every single week. Hit like if you think more people should see this, and drop a comment below. If you could know one truth about the universe, what would it be? I read everything. Now let us begin. Nothing. Absolutely nothing. No light, no darkness, no sound, no silence either. Because even silence requires a place to exist, and there was no place. No time, no space, not a single atom, not a single thought. Just zero, just void. Now think about this. Everything you see tonight, the stars glowing in the sky, the ground beneath your feet, the breath moving through your lungs, all of it started in a single moment. A moment so small that humanity has not yet invented the words to describe it. And from that moment until right now, 13.8 billion years have passed. This documentary is not just the story of the universe. It is your story, because the atoms in your hands were once inside a dying star. The oxygen you are breathing right now was forged inside a supernova explosion billions of years ago. You do not belong to this Earth alone. You belong to this cosmos. And today we are going on that journey from the very beginning, if there even was a beginning. 13.8 billion years ago, a moment arrived that scientists call Planck time. This moment was so incomprehensibly small that if you took 1 second and divided it by 1 billion, then took that result and divided it by 1 billion again, the answer you would get would still be larger than this moment. And in this moment, something happened that we call the Big Bang. But wait, that name is a little misleading, because it was not a bang. There was no explosion. There was no sound, because sound requires air requires an atmosphere, and an atmosphere requires space, which was only just beginning to exist. What happened was an expansion, a sudden, unimaginable, almost insane expansion where space itself was stretching. It was not expanding into anything. Space was creating itself as it grew. Think of it like a rubber band with dots drawn on it. When you stretch the rubber band, the dots do not move from one place to another. The rubber band itself gets bigger. That is exactly what happened to the universe. In the very first second, the temperature was over 10 trillion degrees Celsius. There was only energy. Pure, raw, unimaginable energy. No protons, no neutrons, nothing solid at all. Just a fireball expanding in every direction at once. Then, within the first 3 minutes, something remarkable happened. This energy began taking its first physical form. Protons and neutrons started forming. Hydrogen atoms, helium atoms. The very first material in the universe was ready. But light, stars, planets, life, all of that was still unimaginably far away. Because after this came something called the Dark Ages, an era that lasted for 200 million years. No stars, no light, nothing. Just a chaotic soup of hydrogen gas and helium, slowly cooling, drifting through absolute darkness. If you were somehow there at that time, which was physically impossible, you would have seen nothing at all. The entire universe was one vast, dark, cold, silent cloud of gas. But something was happening inside that darkness. Gravity, that one force that never stops working, never rests, never gives up. Gas particles were pulling toward each other. Slowly, over millions and millions of years, these gas clouds grew denser and denser and denser, until finally, for the very first time in the history of everything, the very first star ignited. Imagine that moment. The entire universe sitting in darkness for hundreds of millions of years, and then, for the first time ever, a single light. One lonely star. One candle burning in an infinite black ocean. This star, which scientists call a population 3 star, was enormous compared to our sun, thousands of times larger, thousands of times hotter. It was made of only hydrogen and helium because nothing else existed yet. No carbon, no oxygen, no iron. And because of how massive it was, it did not live long. Within just a few million years, it exploded in a supernova. An explosion so powerful it created brand new elements, carbon, oxygen, nitrogen, iron, and scattered them across the universe like seeds thrown into the wind. Those are the exact same elements inside your body right now. Literally, the iron in your blood came from the death of an ancient star. The carbon in your hands is the ash of an ancient explosion. You are not a product of this universe. You are a part of it. And this journey has only just begun. Ahead we will see how those scattered elements came together to form galaxies. How inside one of those galaxies a small, ordinary star built an ordinary planet. And how on that planet, through an extraordinary combination of chance and chemistry, life began. But before we get there, one secret you need to know. Everything we can actually observe and measure in the universe, all the stars, all the planets, all the galaxies, all of it combined, makes up only 5% of what the universe actually contains. The other 95%, we have no idea what it is, where it is, or why it exists. To find out, meet me in part 2. In the last part, we watched the very first star ignite inside a universe that had been completely dark for 200 million years. We watched it explode, scatter its elements across space, and seed the cosmos with the building blocks of everything that would come after. But one star is not a universe. One candle is not a city. So how did we get from that single burning light to the 2 trillion galaxies that exist today? That is exactly where we are going right now. After those first stars exploded, something extraordinary began to happen across the entire universe at the same time. The elements those supernovae scattered started clumping together under gravity. Not quickly. Nothing in space happens quickly. But over hundreds of millions of years, these clouds of gas and newly created elements began pulling themselves together into larger and larger structures. And slowly, the very first galaxies were born. A galaxy is not just a random collection of stars floating together in space. It is something far more organized, far more alive than that. A galaxy is a gravitationally bound system, meaning every single star inside it is connected to every other star through the invisible force of gravity. They orbit together, move together, evolve together. Some galaxies are spiral-shaped, with beautiful sweeping arms of stars rotating around a central core. Some are elliptical, shaped like a smooth, glowing egg. Some are irregular, with no real shape at all, torn apart by ancient collisions or gravitational forces pulling them in different directions. But all of them, no matter what they look like, are home to billions of stars. Our own home galaxy is called the Milky Way, and on a clear night, far from city lights, you can actually see a small piece of it with your naked eye. That faint white band stretching across the sky, that is the edge of our galaxy as seen from the inside. You are literally looking at 200 to 400 billion stars when you look at that band. And our sun, the star that gives us life, is just one of them. One ordinary star sitting about 26,000 light years from the center, in one of the spiral arms, on one small planet, with one species that recently figured out how to ask questions about all of it. Now here is something that will genuinely make your brain hurt for a moment. The Milky Way is enormous. If you tried to count every star in our galaxy at a rate of 1 star per second, without sleeping, without stopping, without taking a single break, it would take you over 6,000 years to finish. And the Milky Way is not even a particularly large galaxy. There are galaxies out there that contain over 1 trillion stars. Our galaxy is medium-sized at best, average, unremarkable in the grand scale of the cosmos. And then zoom out further. Beyond the Milky Way, there are 2 trillion galaxies in the observable universe alone. 2 trillion. The number is so large it stops feeling like a number and starts feeling like a concept your mind simply refuses to fully accept. If every single grain of sand on every single beach and every single desert on planet Earth were counted, that total would still be less than the number of stars in the observable universe. We are not just small. We are small in a way that has no good human reference point. But here is what makes this even more astonishing. All of those 2 trillion galaxies are not randomly scattered through space like confetti thrown into a room. They follow a structure, a pattern so vast and so intricate that when scientists first mapped it, they could not believe what they were seeing. They called it the cosmic web. The cosmic web is exactly what it sounds like. Imagine the largest spider web you have ever seen, and then scale it up to the size of the entire observable universe. Long thread-like filaments of gas and dark matter stretch across hundreds of millions of light years, connecting massive clusters of galaxies at the points where the threads cross. And between those filaments, between those threads, are vast empty regions called cosmic voids, where almost nothing exists at all. Billions of light years of almost complete emptiness. The universe is mostly empty space, punctuated by thin, glowing threads of matter, and it looks, at the largest scale, almost biological. Almost like a brain, almost like a living thing. Our Milky Way sits within a small cluster of galaxies called the local group. This group contains about 54 galaxies, most of them small dwarf galaxies, all bound together gravitationally. The largest members are the Milky Way and our nearest large neighbor, the Andromeda Galaxy, which sits about 2.5 million light years away from us. That means the light you would see if you looked at Andromeda tonight left that galaxy 2.5 million years ago, when early humans were just beginning to walk upright on the African savanna. You are not seeing Andromeda as it is. You are seeing it as it was, in a past so ancient it barely registers as real. And here is the part that nobody talks about at dinner, but absolutely should. Andromeda is heading straight toward us. Right now, as you watch this, Andromeda is moving in our direction at about 110 kilometers per second. In roughly 4.5 billion years, Andromeda and the Milky Way will collide and eventually merge into a single massive elliptical galaxy. The night sky during that collision would be unlike anything any human has ever witnessed. New stars would be born by the thousands as gas clouds compress and ignite. Supernovae would light up the sky constantly, 2 entire galaxies becoming one, in a slow-motion cosmic dance lasting hundreds of millions of years. Do not panic though. By the time that happens, our sun will be nearing the end of its own life. And because galaxies are mostly empty space, the actual chances of individual stars physically colliding is extremely low. The galaxies will pass through each other, orbit, fall back, and eventually settle into one. Violent by cosmic standards, but silent and slow by any human standard. What this tells us is that the universe is not static. It is not a fixed painting hanging on a wall. It is dynamic, moving, collapsing, expanding, colliding, evolving, every single second of every single day, across scales we can barely begin to imagine. Galaxies are not permanent. They are characters in a story, and that story is still being written. And the next chapter of that story is the one closest to home. Because inside our galaxy, inside one of its spiral arms, something special happened 4.6 billion years ago. A cloud of gas and dust began to collapse. And what it built changed everything. That is exactly where part 3 begins. We left off watching the universe build itself from the outside in. 2 trillion galaxies arranged into a cosmic web, each one containing billions of stars, all of it moving, evolving, colliding, changing over billions of years. But now we zoom in, way in, past the great galaxy clusters, past the filaments of the cosmic web, past the edge of the Milky Way, down into one of its spiral arms, to a relatively quiet, relatively unremarkable corner of our galaxy, where 4.6 billion years ago, something began that would eventually lead to you sitting here watching this video tonight. It started with a cloud, a massive, cold, slowly rotating cloud of gas and dust drifting through space. Mostly hydrogen, some helium, and small amounts of heavier elements left behind by stars that had already lived and died before our solar system ever existed. This cloud had been drifting for a long time, just floating, doing nothing dramatic, until something disturbed it. Scientists believe it may have been the shockwave from a nearby supernova, a dying star's final explosion, sending a ripple through space that nudged this cloud just enough to start a chain of events that would take billions of years to fully play out. That nudge was all gravity needed. Once the cloud started collapsing inward, gravity took over and never let go. The outer edges of the cloud began falling toward the center, pulled by the combined gravitational attraction of all the material inside. As the cloud collapsed, it began spinning faster, the same way a figure skater pulls their arms in and starts rotating more rapidly. The cloud flattened out into a spinning disk, with the vast majority of materials spiraling down toward the center, and the rest spread out in a wide flat ring around it. At the center, things were getting intense. The gas and dust piling in from every direction was being compressed more and more tightly, and as any gas compresses, it heats up. The temperature at the center of this collapsing cloud rose steadily over millions of years. 1 million degrees, 10 million degrees, and then, at around 15 million degrees Celsius, something happened that had happened billions of times before across the universe, but was happening here for the first time in this corner of the galaxy. The hydrogen atoms at the center were squeezed so tightly together that they began fusing. Hydrogen nuclei slamming into each other with enough force to stick together and form helium, releasing an enormous burst of energy in the process. Nuclear fusion had ignited. Our sun was born. In that single moment, a star switched on that would burn for 10 billion years. Our sun is not particularly large or small. It is a yellow dwarf star, what scientists call a G-type main sequence star, sitting comfortably in the middle of the stellar size chart. It is not the hottest star, not the brightest, not the biggest, but it is ours, and it is extraordinarily well suited for what came next. It burns steadily and consistently, without massive violent flares that would sterilize nearby planets, and it sits in a stable region of the galaxy away from the intense radiation near the galactic center. In terms of building a solar system capable of supporting life, our sun hit nearly every favorable condition available. Meanwhile, in the disk of gas and dust spinning around the newborn sun, another process was already underway. The material in that disk was not just floating there passively. Dust particles were colliding with each other, and when they collided at low enough speeds, they stuck together. Small clumps formed. Those clumps collided with other clumps and grew larger. Over millions of years, these growing bodies, called planetesimals, swept up more and more material along their orbital paths. The bigger they got, the stronger their gravitational pull, and the stronger their gravitational pull, the more material they attracted. A runaway process of growth that gradually built up larger and larger bodies until finally, after tens of millions of years, proper planets had formed. The inner solar system, close to the sun where temperatures were too high for ice and gases to remain solid, built rocky planets. Mercury, Venus, Earth, and Mars, all made primarily of rock and metal, the materials that could withstand the heat. Further out, beyond what scientists call the frost line, where temperatures dropped low enough for water ice and other volatile compounds to remain solid, the building blocks were far more abundant. This allowed the outer planets to grow much larger, accumulating not just rock and metal but enormous envelopes of gas, becoming the gas giants we know today. Jupiter, Saturn, Uranus, and Neptune. Jupiter deserves a special mention here, because Jupiter may be one of the reasons life exists on Earth at all. Jupiter is so massive, more than twice the mass of all the other planets in our solar system combined, that its gravitational influence is enormous. Over billions of years, Jupiter has acted as a kind of cosmic shield, its gravity deflecting and capturing many of the asteroids and comets that might otherwise have bombarded the inner solar system far more frequently. Without Jupiter sitting out there pulling dangerous objects away from us, Earth may have been struck so many times by massive impactors that complex life might never have had a chance to develop. We may owe our existence, in part, to a planet we will never set foot on. But the story of Earth itself is the one that matters most for us, and it is wilder than almost any story you have ever heard. When Earth first formed around 4.5 billion years ago, it looked nothing like it does today. There were no oceans, no atmosphere, no continents, no life of any kind. It was a ball of molten rock, constantly bombarded by asteroids and other debris left over from the solar system's formation. Its surface a churning ocean of liquid magma glowing red and orange under a sky full of debris still raining down from above. Then, about 100 million years after Earth formed, something enormous hit it. A Mars-sized body, which scientists have named Theia, slammed into the early Earth in a collision so violent it partially melted both objects, ejected an enormous amount of material into orbit around Earth, and set the stage for something completely unexpected. That ejected material, over thousands of years, gradually coalesced under gravity into a single round body orbiting our planet, our moon. The moon was not always there. It was built from the ruins of a collision, and its presence turned out to matter enormously, stabilizing Earth's axial tilt and creating the tides that may have played a critical role in driving the chemistry that eventually led to life. Everything in our solar system is connected. Every planet, every moon, every asteroid, every comet tells part of the same story. A story that began with a nudge to a cloud of gas 4.6 billion years ago and ends, at least for now, with a species on the third planet from the sun looking back up at the stars and asking how all of this happened. The universe built this solar system piece by piece over millions of years, and then it built something even more remarkable on the surface of one small rocky world. And that is exactly where Part 4 takes us. We ended Part 3 standing on the surface of a newly formed Earth, a boiling, molten, battered rock being pounded by asteroids, with no oceans, no air, no life, and absolutely no indication that any of that was ever going to change. If you had looked at Earth 4.5 billion years ago and been asked to predict its future, the honest answer would have been that it looks like every other dead rock in the solar system. Nothing special, nothing promising, just another planet formed from debris, slowly cooling in the dark. And yet, something happened here that, as far as we know, has never been confirmed to have happened anywhere else in the entire observable universe. Life began. How it began is one of the greatest unsolved questions in all of science. We have theories, we have evidence, we have incredibly compelling research pointing in certain directions, but we do not have a complete answer. And that is not a failure of science. That is an honest reflection of just how staggeringly complex and ancient this question is. We are trying to reconstruct a chemistry experiment that happened nearly 4 billion years ago on a planet that has been geologically active ever since, erasing most of the evidence. The fact that we know as much as we do is itself extraordinary. So let us walk through what we do know. After the chaos of Earth's formation began to settle, somewhere around 4.4 billion years ago, the surface started to cool. As it cooled, water vapor in the early atmosphere began condensing and falling as rain. And it rained, in a way that is almost impossible to imagine for potentially millions of years. Water also arrived from space, delivered by comets and water-rich asteroids bombarding the young Earth during a period called the Late Heavy Bombardment. Slowly, the oceans filled, and with liquid water covering much of the planet's surface, the chemical stage was set for something remarkable. Water is not just a convenience for life. It is, as far as we understand, an absolute requirement. It is an extraordinary solvent, meaning it dissolves more substances than almost any other liquid, allowing complex chemistry to happen that simply cannot happen in dry environments. It remains liquid across a wide range of temperatures. It expands when it freezes, which means ice floats rather than sinking, which means frozen lakes and oceans develop an insulating layer on top rather than freezing solid from the bottom up, which protects whatever chemistry is happening in the liquid water below. Every single one of these properties seems almost specifically designed to make life possible, though of course they were not designed at all. They are simply the properties water happens to have, and life evolved to take advantage of all of them. The earliest evidence we have for life on Earth dates to around 3.7 to 3.8 billion years ago, in the form of microfossils and chemical signatures found in ancient rocks in Greenland and Australia. These were not complex creatures. They were single-celled microorganisms, simpler than almost anything alive today, with no nucleus, no complex internal structures, just a membrane surrounding a collection of molecules capable of the two things that define life, taking in energy from the environment and making copies of themselves. But simple as they were, their existence required something extraordinary to happen first: the origin of the very first self-replicating molecule. This is where things get genuinely mind-bending. For life to begin, you need molecules that can copy themselves, because without self-replication there is no inheritance. Without inheritance there is no evolution, and without evolution there is no way to build complexity over time. The molecule that does this job in all life on Earth today is DNA. But DNA is itself extraordinarily complex and cannot replicate without the help of proteins, and proteins cannot be built without instructions from DNA. It is a chicken and egg problem of almost dizzying depth. Which came first, the DNA or the proteins it needs to function? The leading hypothesis that has emerged to resolve this is called the RNA world hypothesis. RNA is a molecule similar to DNA, but simpler, and crucially, RNA can do both jobs. It can carry genetic information like DNA does, and it can also act as a catalyst to drive chemical reactions like proteins do. Scientists have shown in laboratory experiments that RNA molecules can spontaneously form from simpler chemical building blocks under conditions that likely existed on the early Earth, and that certain RNA molecules can actually copy themselves without any external help. The idea is that before DNA and proteins existed, there was a world of self-replicating RNA molecules, gradually evolving and growing more complex, until eventually the system we know today, with DNA storing information and proteins doing the chemical work, emerged from that earlier RNA-based chemistry. But where did this chemistry happen? Where was the cradle of life? There are two main competing ideas, and both of them are fascinating. The first is the primordial soup hypothesis, originally proposed by scientists Alexander Oparin and J.B.S. Haldane in the 1920s, which suggests that the early ocean surface, energized by lightning, ultraviolet radiation from the sun, and heat, provided the right chemical conditions for organic molecules to form and eventually combine into self-replicating systems. Famous experiments by Stanley Miller and Harold Urey in 1953 showed that simply passing electrical sparks through a mixture of gases thought to represent the early Earth's atmosphere produced amino acids, the building blocks of proteins, in just a few days. The raw ingredients for life can form spontaneously from simple chemistry. That much is now beyond doubt. The second hypothesis focuses on deep-sea hydrothermal vents, particularly a type called alkaline hydrothermal vents, which were discovered more recently and have generated enormous excitement in the origins of life research community. These vents, found on the ocean floor, release warm alkaline fluid that mixes with the cold acidic ocean water, creating natural chemical gradients, essentially natural batteries, that could have driven the chemistry needed to build the first biological molecules. The rocky structures around these vents are full of tiny interconnected pores, almost like miniature cells, that could have concentrated chemicals and provided a protected environment for early chemistry to develop. Many researchers today believe that alkaline hydrothermal vents are among the most plausible locations for life's origin on Earth. What happened next, once those first self-replicating molecules appeared, was the most consequential process in the history of this planet. Evolution. Once you have molecules that can copy themselves, but make occasional errors in copying, and once some of those errors happen to make the molecule slightly better at copying itself, you have natural selection. The better copiers copy more. The worse copiers disappear. Over millions of generations, complexity accumulates. Membranes form around molecules, creating the first cells. Cells develop more sophisticated internal machinery. Some cells learn to capture energy directly from sunlight through photosynthesis. And then, around 2.4 billion years ago, those photosynthesizing cells changed everything with a byproduct of their metabolism that transformed the entire planet. Oxygen. For most of Earth's early history, there was virtually no free oxygen in the atmosphere. The first photosynthetic organisms, cyanobacteria, began producing oxygen as a waste product, and over hundreds of millions of years they pumped so much of it into the atmosphere that it fundamentally changed the chemistry of the air, the oceans, and the rocks. This event, called the Great Oxidation Event, was catastrophic for the microorganisms that had evolved in an oxygen-free world. For them, oxygen was toxic, a poison flooding their environment. But for the organisms that could tolerate it or even use it, oxygen opened up a new way of extracting energy from food that was far more powerful and efficient than anything that had come before. Aerobic respiration, breathing oxygen, is what powers almost every complex organism alive on Earth today, including you. From that point forward, the story of life on Earth is one of relentless, breathtaking, occasionally horrifying complexity building upon complexity. Simple cells gave rise to cells with a nucleus. Single cells began forming cooperative colonies. Those colonies evolved into the first multicellular organisms. And then, in a period of geological time called the Cambrian explosion, around 540 million years ago, life seemed to suddenly explode into an enormous diversity of complex body forms, with eyes, limbs, shells, nervous systems, all appearing in the fossil record in what amounts to the blink of an eye in geological time. From there, life colonized the land, took to the air, survived multiple mass extinctions, and eventually, after 3.8 billion years of evolution, produced a species capable of looking back at the stars and tracing its own origin all the way back to the Big Bang. You are the universe becoming aware of itself. You are 13.8 billion years of cosmic history looking in a mirror, and the story is nowhere near finished. Because as remarkable as life on Earth is, the question that haunts every scientist who studies the cosmos is the same one that is probably already forming in your mind right now. If it happened here, on this one small planet, in this one ordinary solar system, in this one unremarkable corner of one galaxy among 2 trillion, did it happen somewhere else too? Are we alone? That is exactly where Part 5 is going to take us. Everything we have covered so far has been building toward this moment. We watched the universe born from nothing, watched the first stars ignite in absolute darkness, watched galaxies assemble themselves into a cosmic web spanning billions of light years, watched our own solar system form from a collapsing cloud of gas, and watched life crawl out of the chemistry of a young ocean on a small rocky planet. And now we arrive at the question that has haunted human beings for as long as we have been capable of looking up at the night sky and wondering, are we alone in this universe? Is Earth the single, solitary exception in an otherwise lifeless cosmos? Or is life out there somewhere, waiting to be found, maybe already looking back at us? This is not just a philosophical question anymore. It is an active, urgent, well-funded scientific pursuit. And in the last few decades, the evidence pointing toward the possibility of life beyond Earth has grown more compelling with almost every new discovery we make. We are not at the point where we can say with certainty that alien life exists. But we are absolutely at the point where the idea that Earth is the only living world in the entire universe is starting to look less like humble caution and more like a failure of imagination. Let us start with numbers, because the numbers alone are staggering. There are roughly 2 trillion galaxies in the observable universe. The Milky Way alone contains somewhere between 200 and 400 billion stars. Observations from NASA's Kepler Space Telescope and its successor tests have revealed something that fundamentally changed how scientists think about planets in the universe. Nearly every star has planets. Not some stars, not most stars. Essentially, every single star you see in the night sky is orbited by at least one planet, and many are orbited by several. That means the total number of planets in the observable universe is estimated to be in the range of 1 septillion, which is a 1 followed by 24 zeros. 1 septillion planets. And the question we are really asking is whether life arose on just one of them. Within that enormous number, scientists focus on a subset called potentially habitable planets, worlds that orbit their star at the right distance to allow liquid water to exist on their surface, not too hot, not too cold, sitting in what astronomers call the habitable zone or the Goldilocks zone. Our own estimates suggest there could be tens of billions of potentially habitable Earth-sized planets in the Milky Way alone. Tens of billions. In just our one galaxy. The sheer statistical improbability of all of them being completely lifeless, given what we know about how readily chemistry organizes itself into complex molecules, is something that keeps astrobiologists up at night. But statistics alone are not science. So let us look at what we have actually found. In 1996, a team of NASA scientists announced that they had found possible evidence of ancient microbial life inside a meteorite called ALH 84001, a rock that originated on Mars, was blasted into space by an asteroid impact billions of years ago, drifted through the solar system, and eventually fell to Earth in Antarctica. Inside that meteorite, they found microscopic structures that looked like fossilized bacteria, along with chemical signatures associated with biological processes. The announcement was met with both enormous excitement and enormous skepticism, and to this day the debate over what those structures actually represent has not been fully resolved. But the fact that a rock from Mars contained anything remotely suggestive of biology was a turning point in how seriously the scientific community began treating the search for extraterrestrial life. Mars itself remains one of our most compelling targets. Ancient Mars, around 3 to 4 billion years ago, was a very different world from the frozen, thin-air desert it is today. It had liquid water flowing across its surface, river valleys, lake beds, and possibly even an ocean covering much of its northern hemisphere. Its atmosphere was thicker, its climate was warmer, and the conditions on its surface were in many ways similar to early Earth, right around the time life was first getting started here. If life arose on Earth during that period, it is entirely reasonable to ask whether something similar was happening on Mars at the same time. Mars then dried out, lost most of its atmosphere, and became the cold, barren world we see today. But life, if it ever existed there, may not have simply disappeared. It may have retreated underground, where liquid water may still exist beneath the surface, kept warm by geothermal heat, sheltered from the radiation that now bombards the Martian surface. NASA's Perseverance rover is on Mars right now, specifically searching for signs of ancient microbial life in the sediments of an ancient lake bed called Jezero Crater. The samples it is collecting will eventually be returned to Earth for analysis. We may be less than a decade away from having a definitive answer about life on Mars. But Mars is just the beginning. Some of the most exciting targets in the search for life are not planets at all. They are moons. Jupiter's moon Europa is covered by a thick shell of ice, beneath which scientists are highly confident there is a global liquid water ocean, kept warm by the tidal flexing caused by Jupiter's enormous gravitational pull kneading the moon's interior like dough. This ocean has likely existed for billions of years. It is in contact with a rocky seafloor. It has an energy source. It has liquid water. Those are three of the key ingredients we associate with life as we know it, and Europa has all three. NASA's Europa Clipper mission launched in 2024 and is currently on its way to study this moon in unprecedented detail. What it finds will reshape our understanding of where in the solar system life might exist. Saturn's moon Enceladus is equally extraordinary. In 2005, NASA's Cassini spacecraft made one of the most shocking discoveries in the history of planetary science when it flew through enormous plumes of water vapor and ice particles erupting from cracks near Enceladus's south pole and shooting hundreds of kilometers into space. Beneath that icy surface, there is another global liquid water ocean, and when Cassini analyzed those plumes, it found water, salts, silica particles, carbon dioxide, methane, molecular hydrogen, and complex organic molecules, including some that on Earth are associated exclusively with biological or hydrothermal chemical processes. Enceladus is actively venting the contents of its subsurface ocean into space. It is essentially offering us a sample of its ocean without us even having to land. A future mission that flies through those plumes with more sensitive instruments could potentially detect signs of microbial life directly. The implications of that are almost too large to process calmly. Then there is Titan, Saturn's largest moon and one of the strangest worlds in the solar system. Titan has a thick nitrogen atmosphere, denser than Earth's, and on its surface there are rivers, lakes, and seas, not of water, but of liquid methane and ethane. It rains methane on Titan. Methane flows across its surface and collects in Great Lakes near its poles. Scientists have proposed that life on Titan, if it exists at all, would be chemically completely unlike life on Earth, using liquid methane as its solvent instead of water, breathing hydrogen instead of oxygen, and producing methane as a metabolic byproduct. We have no idea if such exotic life is possible, but we also have no strong theoretical reason to rule it out. NASA's Dragonfly mission, a rotorcraft lander, is scheduled to arrive at Titan in the 2030s to explore its surface directly. Whatever it finds, it will be unlike anything humanity has ever encountered. Beyond our solar system, the search for life takes the form of studying exoplanet atmospheres for what scientists call biosignatures, chemical signs in a planet's atmosphere that could indicate the presence of life. When a planet passes in front of its star, a tiny fraction of the star's light filters through the planet's atmosphere, and the specific wavelengths of light absorbed by that atmosphere tell us what molecules are present. Detecting oxygen alongside methane in an exoplanet's atmosphere, for example, would be a powerful potential biosignature because those two gases react with each other and destroy each other quickly. So finding both together in large quantities would suggest something is actively replenishing them. And on Earth, the thing replenishing both is life. The James Webb Space Telescope, the most powerful observatory humanity has ever built, is already conducting these atmospheric analyses on nearby exoplanets. We have not found definitive biosignatures yet, but the technology is now capable of detecting them if they are there. And then there is SETI, the search for extraterrestrial intelligence, the effort to detect not just microbial life, but technologically advanced civilizations that might be broadcasting their presence through radio waves, laser signals, or other forms of electromagnetic radiation across interstellar distances. Since the 1960s, scientists have been listening to the sky with radio telescopes, searching for a signal that could not have been produced by any natural process. In 1977, a volunteer named Jerry Emmon detected an unusual signal at the Big Ear Radio Telescope in Ohio that was so remarkable, he wrote the word "wow" in the margins of the printout. The wow signal has never been detected again and remains unexplained to this day. It may have been a natural phenomenon. It may have been interference. Or it may have been something else entirely. We simply do not know. What we do know is that the universe is under no obligation to have produced life only once. The chemistry that gave rise to life on Earth, amino acids, nucleotides, lipids, is found throughout the cosmos. Complex organic molecules have been detected in interstellar clouds, in meteorites, in comets, floating freely through space between the stars. The building blocks of life appear to be not rare, but common. Extraordinarily, almost universally common. And if the building blocks are everywhere, and if planets are everywhere, and if liquid water turns out to be far more common in the solar system than we once thought, then the silence of the cosmos becomes not a confirmation of our solitude, but one of the deepest mysteries we have ever faced. Where is everybody? Why haven't we heard anything yet? And what would it actually mean for humanity if we did? That question, and the one that follows it, is exactly where Part 6 is going to take us. We ended Part 5 staring at a universe overflowing with the ingredients for life. Billions of potentially habitable planets in our galaxy alone, oceans hiding beneath the ice of moons right here in our own solar system, complex organic molecules drifting freely through interstellar space, and a chemistry that appears to be not rare, but almost embarrassingly common across the cosmos. And yet, despite all of that, despite decades of listening, searching, scanning, and analyzing, we have not found a single confirmed signal, not a single unambiguous sign, not one piece of undeniable evidence that any other intelligent civilization has ever existed anywhere in this universe. Not one. And that silence is not comforting. That silence is one of the most deeply unsettling facts in all of science. Because it has a name, and that name is the Fermi paradox. The story begins in the summer of 1950 at Los Alamos National Laboratory in New Mexico, where a group of physicists were walking to lunch together and having a casual conversation about a recent wave of UFO sightings that had been in the news. The conversation moved through various lighthearted topics until the brilliant Italian-American physicist Enrico Fermi, one of the architects of the nuclear age and a man known for his ability to make extraordinary calculations from very basic assumptions, suddenly went quiet for a moment and then asked a question that stopped the conversation cold. He said, simply, "Where is everybody?" What Fermi meant was this. The universe is 13.8 billion years old. The Milky Way alone contains hundreds of billions of stars, many of them far older than our sun. If even a small fraction of those stars have habitable planets, and if life arose on even a tiny fraction of those planets, and if even a small number of those life forms eventually developed intelligence and technology, then given the age of the universe, at least some of those civilizations should have had billions of years head start on us. Billions of years. A civilization with even a modest head start of a few million years, using technology only slightly more advanced than what we can imagine today, could theoretically have colonized the entire Milky Way galaxy many times over within that time frame. Even traveling at a small fraction of the speed of light, the math works out. The galaxy should, statistically speaking, be teeming with evidence of intelligent life. And yet we see nothing. We hear nothing. We find nothing. Where is everybody? This contradiction between the high probability of extraterrestrial civilizations existing and the complete absence of any evidence for them is the Fermi paradox, and it has generated more serious scientific discussion more philosophical debate, and more genuinely terrifying proposed solutions than almost any other question in modern science. Because every proposed solution to the Fermi paradox, when you follow it to its logical conclusion, says something profound and often deeply unsettling about the nature of life, intelligence, and the long-term future of civilization in this universe. The proposed solutions generally fall into a few broad categories, and it is worth walking through the most compelling ones carefully, because each of them carries implications that go far beyond the abstract question of alien life. The first and perhaps most reassuring category is simply that we have not looked hard enough, long enough, or in the right ways. SETI has been scanning the radio spectrum for decades, but has covered only a tiny fraction of the possible signal frequencies, directions, and signal types that an advanced civilization might use to communicate. Maybe they are sending laser pulses, and we are listening for radio waves. Maybe they are communicating through neutrinos or gravitational waves, or some physical phenomenon we have not even discovered yet. Maybe the signals are there, and we simply lack the instruments or the knowledge to recognize them. This solution is hopeful, and it may well be correct, but it becomes less satisfying the longer the silence continues and the more sophisticated our search technology becomes. The second category involves what scientists call the Great Filter. This concept, introduced by economist Robin Hanson in 1998, proposes that somewhere along the path from simple chemistry to a spacefaring civilization, there is a step, or possibly several steps, that is extraordinarily difficult to cross, so difficult that almost no species ever manages it. Something filters out the vast majority of potential civilizations before they reach the point where they would be visible or detectable to us. The critical and deeply consequential question is where that filter sits on the timeline. Is it behind us or ahead of us? If the Great Filter is behind us, then we have already crossed it. Something in our past was extraordinarily unlikely. So unlikely that we are essentially alone or nearly alone in the universe as a result. The origin of life itself might be that filter. Despite what we said in the last part about organic molecules being common, the actual leap from chemistry to the first self-replicating molecule may be so astronomically improbable that it happens only once or a handful of times in an entire galaxy over the course of billions of years. Or the filter might be the development of the complex eukaryotic cell, the type of cell with a nucleus that all complex life on Earth is built from, an event that took nearly 2 billion years to occur after life first appeared and may have required an extraordinarily unlikely merger between two different types of microorganism. Or perhaps the filter is the development of human-level intelligence itself, which in Earth's history has appeared only once in 4 billion years of evolution and may simply be far rarer than we assume. If the Great Filter is behind us, then the silence of the cosmos is actually good news for humanity. It means we are one of the rare ones. It means we made it through. It means the road ahead, while difficult, is open. But if the Great Filter is ahead of us, the implications are almost too dark to sit with comfortably. In that scenario, there is a step between where we are now and a sustainable spacefaring civilization that virtually every intelligent species fails to cross. Maybe every sufficiently advanced civilization inevitably develops technology that destroys it before it can spread beyond its home world. Nuclear weapons, engineered pandemics, runaway artificial intelligence, climate catastrophe, some combination of all of these. Maybe the development of a certain level of technological power always, inevitably, leads to self-destruction, not because civilizations are uniquely malicious, but simply because the tools powerful enough to reshape a world are also powerful enough to destroy one. And the window between gaining that power and learning to use it wisely is too narrow for most species to survive. This version of the Great Filter would mean that the silence of the cosmos is a warning, that civilizations like ours routinely reach this exact point and then disappear, leaving no trace, no signal, nothing but silence. There is a particular variation of this idea that scientists call the dark forest hypothesis, inspired by a concept from science fiction, but taken seriously by some researchers as a genuine possible explanation for the Fermi paradox. The dark forest hypothesis proposes that the universe is silent not because intelligent life is rare, but because intelligent life is afraid. In a universe where resources are finite and the intentions of unknown civilizations cannot be verified, any sufficiently advanced civilization would quickly realize that broadcasting your existence to the cosmos is extraordinarily dangerous. You cannot know if the civilization receiving your signal is friendly or hostile. You cannot know their technology level or their intentions. And in a situation of that kind of uncertainty, the rational strategy for survival might be to stay silent and hidden, and to eliminate any other civilization you detect before they can eliminate you first. In the dark forest, everybody is hiding, and anybody who reveals themselves gets shot. It is a deeply uncomfortable idea, and it carries the implication that our own radio broadcasts, which have been leaking into space for over a century now, may have already announced our presence to anyone within 100 light years of Earth who happens to be listening. A somewhat more hopeful resolution to the Fermi paradox is what some researchers call the planetarium hypothesis or the zoo hypothesis, which suggests that advanced civilizations do exist, but have made a deliberate choice not to contact us, either because they are observing us without interference the way a scientist observes a specimen, or because there is some kind of agreed-upon protocol among advanced civilizations to leave developing species alone until they reach a certain threshold of technological or social maturity. In this scenario, the silence is not emptiness. It is a waiting room. We are being watched, and at some point, something we do or become will trigger contact. What that threshold might be, nobody knows. Then there is perhaps the most philosophically interesting possibility of all, which is that advanced civilizations do not expand across the galaxy in the way we imagine, because expansion itself stops being appealing at a certain level of technological development. Maybe civilizations turn inward rather than outward, creating extraordinarily rich virtual realities, simulating entire universes within their computing systems, and finding everything they could ever want or explore within the confines of a single planet or a single star system. Maybe the silence is not the silence of absence, but the silence of civilizations so absorbed in their own inner worlds that the physical universe no longer holds much interest. From the outside, such a civilization would look identical to a dead world. What makes the Fermi paradox so genuinely haunting is that every single one of these solutions is plausible, and we currently have no way to determine which one, if any, is correct. Each solution paints a radically different picture of what the universe is, what our place in it is, and what our future might look like. And the answer we eventually find, whether through detecting a signal, finding microbial life on Mars, or simply continuing to hear nothing for another century, will be one of the most consequential discoveries in the history of human thought. But while we wait for that answer, there are other mysteries closer to home that are just as profound and just as unsettling. Because even here on Earth, even within the boundaries of our own planet and our own civilization, there are questions about the nature of reality itself that science is only beginning to develop the tools to approach. Questions about time, about consciousness, about the fabric of space, about what the universe is made of at its deepest level. And those questions are exactly where Part 7 is going to take us. We have traveled far in this documentary. We watched the universe explode into existence from nothing, watched the first stars burn and die, watched galaxies assemble into a cosmic web, watched life crawl out of the chemistry of a young ocean, and spent the last part staring into the unsettling silence of a universe that statistically should be full of voices, but appears to be completely quiet. But now we need to go deeper than any of that, not outward into space, but inward, into the fundamental nature of reality itself. Because the universe is not just made of stars and planets and galaxies. It is made of something far stranger, governed by rules so counterintuitive and so bizarre that even the scientists who discovered them spent years struggling to accept what their own mathematics was telling them. We are going to talk about space, time, and the two great theories that between them describe everything we have ever observed in the physical universe, and yet fundamentally, irreconcilably, disagree with each other. The first of these theories is general relativity, published by Albert Einstein in 1915, and it is one of the most beautiful and radical ideas any human being has ever produced. Before Einstein, the world operated on the physics of Isaac Newton, which described gravity as a force, an invisible pull that massive objects exerted on each other across the emptiness of space. Newton's physics worked extraordinarily well for everyday purposes. It could predict the orbits of planets, the trajectory of cannonballs, the motion of the moon with stunning accuracy. But it had a problem. It treated space and time as a fixed, unchanging background stage on which the events of the universe played out. Space was just empty space, a passive container. Time ticked along at the same rate everywhere, for everyone, always. The universe was a clockwork machine, and space and time were the clock face it ran against. Einstein demolished this picture entirely. What general relativity says is that space and time are not a fixed background. They are not a passive stage. They are themselves physical things, woven together into a single four-dimensional fabric called space-time, and that fabric can bend, curve, stretch, and warp in response to the presence of mass and energy. Gravity is not a force in Einstein's picture. Gravity is the curvature of space-time. When you drop an object and it falls to the floor, it is not being pulled by an invisible force. It is following the straightest possible path through a space-time that has been curved by the mass of the Earth beneath it. The Earth's mass bends space-time, and objects near that mass follow the curves. This is why the moon orbits the Earth and the Earth orbits the sun. They are not being pulled. They are following curves in the fabric of space-time created by each other's mass, like a marble rolling around the inside of a curved bowl. The implications of this idea are staggering and deeply strange. If space-time can be curved by mass, then some of its most fundamental properties, including the rate at which time passes, must also change depending on where you are and how fast you are moving. Time does not tick at the same rate everywhere. Time passes more slowly in stronger gravitational fields. Right now, at this very moment, time is passing slightly faster for you than it is for someone standing at the bottom of a very deep mine shaft, because they are slightly deeper in Earth's gravitational field. The difference is tiny, fractions of microseconds over a lifetime, but it is real, it is measurable, and it has real-world consequences. The GPS satellites orbiting Earth have to constantly correct for the fact that their clocks run faster than clocks on the ground due to being further from Earth's gravitational field. Otherwise, the GPS system would accumulate errors of several kilometers per day and become completely useless. General relativity is not abstract philosophy. It is built into the technology you use every time you navigate anywhere. The most extreme demonstration of curved space-time is, of course, a black hole, which we touched on earlier in this documentary. A black hole is a region where matter has been compressed so densely that the curvature of space-time becomes infinite at the center, a point called the singularity, where our equations break down completely and we lose the ability to predict anything. At the boundary of a black hole, called the event horizon, the curvature of space-time is so extreme that even light, traveling at 300,000 kilometers per second, cannot escape. And time, from the perspective of a distant observer watching something fall into a black hole, appears to slow down and eventually stop completely at the event horizon. The object appears to freeze at the boundary, growing dimmer and redder as the light it emits is stretched by the intense gravitational field, until it fades beyond detectability. Meanwhile, From the perspective of the object falling in, it crosses the event horizon in a finite amount of time and continues inward toward the singularity. Two observers watching the same event, experiencing completely different realities. This is not science fiction. This is what general relativity predicts, and every test we have ever subjected it to has confirmed it to extraordinary precision. In 2015, exactly 100 years after Einstein published general relativity, the LIGO Observatory detected gravitational waves for the first time, ripples in the fabric of space-time itself produced by the collision of two black holes over 1 billion light-years away. Einstein had predicted these waves in 1916, but doubted they would ever be detectable because they are so incredibly faint by the time they reach Earth. The signal LIGO detected distorted space-time by an amount smaller than 1,000th the diameter of a proton. Scientists measured a change in distance smaller than a proton across a detector 4 kilometers long. The fact that we built instruments sensitive enough to detect that is one of the most remarkable technological achievements in human history. And what it confirmed is that space-time is not just a mathematical abstraction. It is a real physical medium that ripples and shakes when massive objects accelerate through it. Now here is where things get truly strange, because at the opposite end of the scale from general relativity, describing the very large, the very massive, the curves of space-time and the orbits of galaxies, sits the other great pillar of modern physics, quantum mechanics. And where general relativity is elegant, geometric, almost classical in its mathematical beauty, quantum mechanics is deeply, fundamentally, almost aggressively weird. Quantum mechanics is the theory of the very small, the physics of atoms and the particles that make them up, and it describes a reality that operates by completely different rules from anything in our everyday experience. In the quantum world, particles do not have definite positions or definite velocities until they are measured. They exist in what is called a superposition, a simultaneous combination of multiple possible states, all of them real in a mathematical sense, until an observation or measurement forces them to settle into a single definite state. This is not a statement about our ignorance of where a particle is. It is a statement about the fundamental nature of reality at the quantum scale. The particle genuinely does not have a definite position until it is measured. Its position before measurement is not a hidden fact waiting to be uncovered. It is genuinely undefined. This idea, known as the Copenhagen interpretation of quantum mechanics, troubled Einstein so deeply that he spent the last decades of his life trying to find a way around it. His objection was famously summarized in his statement that God does not play dice, meaning he refused to accept that the universe at its most fundamental level was governed by irreducible randomness. He believed there must be hidden variables, deeper underlying facts about particles that we simply had not discovered yet, that would restore determinism to physics if we could find them. Experiments conducted decades after Einstein's death, particularly tests of what are called Bell inequalities, have essentially ruled out the kind of hidden variable theories Einstein hoped for. The universe at the quantum scale genuinely appears to be irreducibly random. God, it seems, does play dice. But the strangeness does not stop at superposition. Quantum mechanics also predicts a phenomenon called quantum entanglement, which Einstein memorably called spooky action at a distance, and which he considered so absurd that it must indicate a flaw in the theory. Entanglement occurs when two particles interact in such a way that their quantum states become linked, no matter how far apart they subsequently travel. If you then measure one particle and find it in a particular state, the other particle instantaneously settles into a corresponding state, regardless of the distance between them. Not quickly, not at the speed of light, instantaneously. The measurement of one particle appears to influence the other particle instantly, even if they are on opposite sides of the galaxy. Experiments have confirmed this phenomenon to extraordinary precision, and it is real. Entanglement is not a theoretical curiosity. It is the basis of an entire emerging field of quantum technologies, including quantum computing and quantum cryptography. So here is the profound problem that sits at the heart of modern physics. General relativity describes the universe at large scales with extraordinary accuracy. Quantum mechanics describes the universe at small scales with extraordinary accuracy. Both theories are the most precisely tested and confirmed theories in the history of science, and they are fundamentally incompatible with each other. The mathematical framework of general relativity breaks down when you try to apply it to the quantum scale. The mathematical framework of quantum mechanics does not naturally incorporate the curved space-time of general relativity. When physicists try to combine the two theories to describe situations where both are relevant, such as the interior of a black hole or the first instant of the Big Bang, the mathematics produces infinities and nonsensical results. The two greatest theories ever constructed by human minds cannot both be completely correct because they disagree with each other at the deepest level. Resolving this incompatibility is the central unsolved problem of theoretical physics. The leading candidate for a unified theory is string theory, which proposes that the fundamental constituents of reality are not point-like particles, but tiny one-dimensional vibrating strings of energy, whose different vibrational modes correspond to different particles. String theory naturally incorporates gravity and quantum mechanics in the same mathematical framework, which is remarkable. But it also requires the existence of at least 10 spatial dimensions, with the extra dimensions curled up at scales far too small to detect with current technology. String theory has not yet produced a testable prediction that has been confirmed by experiment, which means it remains a mathematically compelling but physically unverified framework. Another candidate is loop quantum gravity, which attempts to quantize space-time itself, treating space not as a smooth continuous fabric, but as a network of discrete quantum units at the Planck scale. The competition between these approaches and the search for the theory that finally unifies them is where the deepest frontier of physics currently stands. What all of this means, when you step back and take it in, is that we live in a universe whose fundamental nature we do not fully understand. The reality you experience every day, solid objects, flowing time, the pull of gravity, the light from the sun, all of it rests on a foundation of physics that is still being worked out. We have two extraordinary maps of reality, and they cover different territories perfectly, but they do not match up at the borders, and we do not yet have the map that covers everything. But the search for that map has already led us to the most astonishing discovery in the history of cosmology, one that completely changed how we understand the past, the present, and the ultimate fate of the universe. That discovery, and what it means for where everything is headed, is exactly where Part 8 is going to take us. We ended Part 7 standing at the frontier of theoretical physics, staring at two magnificent but irreconcilable theories of reality: general relativity describing the large and quantum mechanics describing the small, neither one wrong, neither one complete, and no unified theory, yet capable of bridging the gap between them. But now we are going to step back from the mathematics and look at the universe as a whole, at the biggest possible picture, because something is happening to the universe right now, something that was discovered less than 30 years ago, and that completely blindsided the scientific community, something that overturned assumptions that had been held since Einstein, something that remains to this day one of the deepest and most unsettling mysteries in all of science. The universe is not just expanding, it is accelerating. Something is pushing it apart faster and faster with every passing moment, and we have absolutely no idea what that something is. To understand why this discovery was so shocking, we need to go back to what scientists expected to find when they started measuring the expansion of the universe in detail in the 1990s. After Edwin Hubble confirmed in 1929 that the universe was expanding, that galaxies were moving away from each other in every direction, the natural question that followed was simple: how will this expansion end? because physicists assumed it would end. The universe is full of matter, and matter has gravity, and gravity pulls things together. So the expansion that began at the Big Bang should be slowing down over time, gradually decelerating as the collective gravitational pull of all the matter in the universe works against it, like a ball thrown upward that slows as gravity pulls it back. The only real question was whether there was enough matter in the universe for gravity to eventually halt the expansion completely and pull everything back together in what cosmologists called the Big Crunch, a reverse Big Bang, or whether the expansion would slow but never quite stop, with the universe coasting outward forever but at an ever-decreasing rate. In the late 1990s, two independent teams of astronomers set out to measure exactly how much the expansion was decelerating. They did this by observing a particular type of exploding star called a Type I supernova. These supernovae are extraordinarily useful to cosmologists because they always explode with almost exactly the same intrinsic brightness, making them what astronomers call standard candles. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate exactly how far away it is. By measuring Type I supernovae at enormous distances, billions of light years away, the two teams could compare how fast the universe was expanding at different points in its history, effectively looking back in time to see how the expansion rate had changed. They expected to find deceleration. They expected the expansion to be slowing down. What they found instead stopped them cold. The universe was not decelerating. It was accelerating. The expansion was not slowing down under the influence of gravity. It was speeding up. Galaxies were flying apart from each other faster now than they were a billion years ago, and faster a billion years ago than they were a billion years before that. Something was pushing the universe apart, overwhelming gravity on the largest scales, and driving an accelerating expansion that showed no signs of stopping. The discovery was so unexpected, so contrary to everything the teams had anticipated finding, that both groups spent months checking and rechecking their data before publishing, convinced they must have made an error somewhere. They had not. The accelerating expansion was real. It was confirmed by multiple independent lines of evidence. And in 2011, the leaders of both teams were awarded the Nobel Prize in Physics for the discovery. The name given to whatever is causing this accelerating expansion is dark energy, and it is perhaps the most mysterious substance or phenomenon in the history of science, because we know almost nothing about it beyond the fact that it exists and that it currently makes up approximately 68% of the total energy content of the observable universe. Let that sink in for a moment. The thing we understand least about the universe, the thing we cannot detect directly, cannot create in a laboratory, cannot describe with any existing theory in a fully satisfying way, makes up more than 2/3 of everything there is. All the matter in the universe, every star, every planet, every galaxy, every atom, every particle of dust drifting between the stars, makes up only about 5% of the universe's total energy content. Dark matter, which we know exists because of its gravitational effects, but which we also cannot see or directly detect, makes up roughly 27%. And dark energy, the most abundant and the most mysterious component of all, makes up the remaining 68%. We are, in the most literal possible sense, living in a universe we cannot see and do not understand. The leading theoretical candidate for what dark energy might be goes back to Einstein himself, who in 1917 introduced into his equations of general relativity a term he called the cosmological constant, represented by the Greek letter lambda. Einstein added this term not because he had any physical reason to believe it was real, but because without it his equations predicted a dynamic universe, one that was either expanding or contracting, and Einstein at the time believed the universe was static and eternal. He used the cosmological constant as a kind of mathematical fudge factor to keep his equations from predicting a changing universe. When Hubble discovered the expansion of the universe in 1929, Einstein called the cosmological constant his greatest blunder and removed it from his equations. But the irony is that the cosmological constant appears to be real after all. It represents what physicists call the energy of empty space itself, the idea that the vacuum of space is not truly empty, but has an inherent energy density that does not dilute as space expands. As the universe grows larger, more empty space is created, and with it comes more of this vacuum energy, providing an ever-increasing push against gravity that drives the accelerating expansion. In this picture, dark energy is not a substance filling space. It is a property of space itself. The problem is that when physicists try to calculate what the energy density of the vacuum should be using quantum mechanics, the answer they get is not close to the observed value of dark energy. It is off by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. This discrepancy between the theoretically predicted value and the observed value of the cosmological constant is described by physicists as the worst prediction in the history of science, and it tells us that our current understanding of either quantum mechanics or the nature of empty space, or quite possibly both, is fundamentally incomplete in some deep way we have not yet identified. Alternative explanations for dark energy exist and are actively being researched. One class of models involves a dynamic field called quintessence, a kind of energy field that permeates all of space, but whose density and properties change over time, unlike the static cosmological constant. In quintessence models, dark energy is not a fixed property of space-time, but an evolving component that has varied throughout the history of the universe and will continue to change in the future. Recent observations from several large-scale surveys of the universe have produced hints that the equation of state of dark energy, the relationship between its pressure and its energy density, may not be exactly consistent with a simple cosmological constant and may be evolving over time. These hints are not yet statistically strong enough to constitute a definitive detection of dynamic dark energy, but they are intriguing enough that multiple major upcoming observational campaigns are specifically designed to test them. If dark energy turns out to be dynamic rather than constant, it would rule out the cosmological constant as an explanation and open the door to entirely new physics. There is another possibility that is even more radical, one that a small but growing number of physicists take seriously. Perhaps dark energy does not exist as a separate entity at all. Perhaps the accelerating expansion is telling us that our theory of gravity, general relativity, breaks down on cosmological scales in a way we have not accounted for. Modified gravity theories propose adjustments to Einstein's equations that would naturally produce an accelerating expansion without requiring any exotic energy component. Some of these theories also make different predictions from general relativity for the growth of cosmic structure, the way matter clumps together over time to form galaxies and galaxy clusters, providing a potential observational test. So far, general relativity has passed every test we have subjected it to with extraordinary precision, but those tests have mostly been conducted in the relatively dense environments of our solar system and nearby binary star systems. The behavior of gravity on truly cosmic scales, across billions of light years, is much less well constrained, and there remains genuine scientific room for modifications. Whatever dark energy turns out to be, its existence has profound implications for the ultimate fate of the universe. And those implications are, depending on your temperament, either deeply sobering or strangely beautiful. If dark energy is a cosmological constant and continues to drive an accelerating expansion indefinitely, the fate of the universe follows a trajectory called the Big Freeze or heat death. Over the next tens of billions of years, the accelerating expansion will push galaxies beyond each other's observable horizons, isolating each galaxy cluster in its own expanding bubble of space-time. Stars will continue to burn, But new star formation will slow as gas is consumed and not replenished. One by one, over trillions of years, the stars will exhaust their fuel and go dark, leaving behind white dwarfs, neutron stars, and black holes. The universe will grow progressively colder and darker. Over unimaginable timescales, on the order of 10 to the power of 40 years, even the white dwarfs and neutron stars will decay through quantum mechanical processes. Black holes will slowly evaporate through Hawking radiation, the last of them disappearing after perhaps 10 to the power of 100 years. And then there will be nothing left but a cold, dark, infinitely expanding void, populated only by the faintest whispers of radiation, approaching but never quite reaching a state of perfect thermodynamic equilibrium. No gradients of temperature or energy to drive any process. No motion, no change, no time in any meaningful sense. The universe will not end with a bang, but with an infinite, silent, featureless stillness. If dark energy is instead dynamic and grows stronger over time, the fate could be even more dramatic. In a scenario called the Big Rip, a strengthening dark energy could eventually overcome not just the gravity holding galaxy clusters together, but the gravity holding individual galaxies together, then the gravity holding solar systems together, then the electromagnetic forces holding planets and rocks and molecules, and finally atoms together, tearing apart all structure in the universe right down to the subatomic level in a finite amount of time, ending everything in a final catastrophic unraveling of space-time itself. Current observations do not favor the Big Rip, but they cannot entirely rule it out either. And if the hints of dynamic dark energy that current surveys are beginning to detect turn out to be real and point in the right direction, there is even a possibility that dark energy could eventually reverse, weakening and then becoming attractive rather than repulsive, leading to a scenario called the Big Crunch where the expansion eventually halts and reverses, with all the matter in the universe falling back together in a mirror image of the Big Bang. Some theorists have proposed that such a Big Crunch could itself trigger a new Big Bang, with the universe bouncing rather than ending, cycling through expansions and contractions across eternal time in what is called a cyclic cosmology. In this picture, our universe is not the first and will not be the last. It is one cycle in an infinite series, each one beginning in a Big Bang and ending in a Big Crunch, with the seeds of the next cycle planted in the death of the previous one. We do not know which of these fates awaits the universe. What we know is that the answer depends entirely on the nature of something we cannot see, cannot touch, cannot directly measure, and cannot yet explain with any existing theory. Dark energy is not just a cosmological curiosity. It is the force that will determine the ultimate destiny of everything that exists. And the fact that we discovered it less than 30 years ago, and that it makes up 68% of the universe, and that we still have no satisfying explanation for what it is, should be a reminder of how young our understanding of the cosmos truly is, and how much remains to be discovered. Because if the last century of physics has taught us anything, it is that every time we thought we understood the universe turned out to be far stranger, far richer, and far more surprising than we had imagined. And that lesson has never been more relevant than when we turn to the last great frontier, the one that may be closer to home than any of the others. That frontier is consciousness itself, and the question of what it means for the universe to be aware of its own existence. That is exactly where Part 9 is going to take us. We have spent 8 parts of this documentary traveling outward, across scales that beggar the imagination, from the quantum foam at the smallest conceivable level of reality all the way to the cosmic web spanning hundreds of millions of light years, from the first moment of the Big Bang to the last evaporating black hole in the far future of the universe. We have confronted mysteries that have humbled the greatest minds in human history: dark energy, dark matter, the incompatibility of our two best theories of physics, the the silence of the cosmos, the origin of life itself. But now we need to turn around. We need to look not outward but inward, because there is a mystery sitting right here, inside every human skull on this planet, that is in many ways just as deep and just as unresolved as anything we have encountered in the cosmos. That mystery is consciousness, the simple, staggering, almost unbearably strange fact that the universe, through the mechanism of biological evolution on at least one small planet, has produced entities that are aware of their own existence, that can ask questions about their own nature, that can look up at the stars and wonder where they came from. What is that? How does that happen? And what does it mean? The question of consciousness is often called the hard problem, a term coined by philosopher David Chalmers in 1995, and the name is not an exaggeration. The hard problem is not about explaining how the brain processes information, how it integrates sensory data, how it stores memories, how it produces behavior. Those are difficult scientific questions, but they are in principle tractable. We can imagine, at least in outline, how sufficiently sophisticated information processing could produce all of those functions. The hard problem is about something else entirely. It is about why any of that information processing is accompanied by subjective experience at all. Why is there something it is like to see the color red, rather than just a brain mechanism that detects and processes a particular wavelength of light? Why does pain feel like something, rather than just triggering avoidance behavior? Why is there an inner life at all, rather than just a very sophisticated biological machine operating in the dark? You could, in principle, imagine a universe where all the same physical processes happened, all the same neurons fired, all the same behaviors occurred, all the same words were spoken, but where there was no inner experience accompanying any of it. No one home, just processing, with no experiencer. Philosophers call such hypothetical beings philosophical zombies, and the fact that we can coherently imagine them without logical contradiction is what makes the hard problem hard. If consciousness were simply the result of a certain kind of information processing, you would not be able to coherently imagine the same processing happening without consciousness. The fact that you can suggest that consciousness is something over and above the physical processes, something that requires an additional explanation that our current scientific framework does not provide. Neuroscience has made extraordinary progress in mapping the correlates of consciousness, the specific patterns of brain activity that accompany specific conscious experiences, but correlation is not explanation. Knowing which neurons fire when you see red does not explain why firing neurons produce the experience of redness rather than nothing at all. The gap between the objective third-person description of brain processes and the subjective first-person reality of experience remains completely unbridged, and there is genuine disagreement among scientists and philosophers about whether it can ever be bridged within the framework of current science, or whether bridging it will require a revolution in our understanding of nature at least as profound as the ones brought about by quantum mechanics and general relativity. Several serious scientific and philosophical frameworks have been proposed to address the hard problem, and they are worth understanding because each of them, if true, would have profound implications not just for neuroscience, but for our entire understanding of what the universe is and what our place in it is. The first and currently most mainstream view among neuroscientists is a family of positions broadly called physicalism or materialism, which holds that consciousness is entirely a product of physical brain processes, that there is nothing over and above the neurons and their electrochemical activity, and that the subjective feeling of experience is either identical to certain brain states or emerges from them in a way that, while not yet explained, is in principle explicable within the framework of physical science. On this view, the hard problem is hard but not impossible, and neuroscience will eventually crack it the way it has cracked other seemingly intractable mysteries about the brain. A more radical view, which has been gaining serious traction among a growing number of philosophers and some scientists, is called panpsychism. Panpsychism is the idea that consciousness, or at least some proto-conscious experiential property, is a fundamental feature of reality, present not just in brains, but in all matter to varying degrees. In the panpsychist view, the reason brains are conscious is not that they do something magical that other physical systems do not do, but that they integrate and organize a fundamental experiential property that is present everywhere, in simpler forms, throughout nature. An electron does not have rich inner experiences the way you do, but it has some infinitesimally simple form of experience or interiority that is the seed of what becomes, when organized in sufficiently complex ways by evolution, the rich conscious life of a human being. Panpsychism sounds bizarre at first encounter, and it has historically been dismissed as mysticism, but in recent years it has been taken increasingly seriously by mainstream philosophers of mind and even some physicists, precisely because it offers a way to address the hard problem without either denying the reality of subjective experience or invoking anything supernatural. If experience is a fundamental feature of reality like mass or charge, then the existence of conscious beings is no more mysterious than the existence of massive objects or electrically charged particles. Related to panpsychism, but emerging from a different direction, is a framework called Integrated Information Theory, or IIT, developed by neuroscientist Giulio Tononi. IIT proposes that consciousness is identical to a particular kind of integrated information measured by a quantity called phi, and that any physical system that integrates information in the right way has some degree of consciousness proportional to its phi value. On this theory, consciousness is not unique to biological brains. Any system with sufficient integrated information, whether biological or silicon-based, natural or artificial, has conscious experience. A very simple system like a thermostat has an almost negligible but non-zero consciousness. A human brain has an enormous phi value and correspondingly rich conscious experience. IIT makes specific mathematical predictions about which physical systems are conscious and which are not, and some of those predictions conflict with mainstream neuroscientific intuitions in striking ways. For example, IIT predicts that certain simple feed-forward computational systems, even very powerful ones, might have low or zero consciousness, while certain simpler but more highly integrated biological structures might be highly conscious. Whether IIT is correct remains deeply contested, but its existence as a serious, mathematically formulated scientific theory of consciousness is a sign of how far the field has come from dismissing the question entirely. And then we arrive at one of the most genuinely mind-bending ideas in modern intellectual life, one that began as a philosophical thought experiment, but has been taken with increasing seriousness by physicists, cosmologists, and technologists over the past 2 decades. The simulation hypothesis. The idea, most famously articulated by philosopher Nick Bostrom in 2003, goes like this. Assume that it is possible, in principle, to run detailed computer simulations of conscious beings, simulations detailed enough that the beings inside them have genuine subjective experiences and believe themselves to be real. If that is possible, then any sufficiently advanced civilization would eventually have the computational power to run enormous numbers of such simulations. If even one civilization in the history of the universe reaches that level of technological development and runs many simulations, then the number of simulated conscious beings in existence would vastly outnumber the number of non-simulated conscious beings. And if that is true, then the simple statistical argument is that any given conscious being, including you, is far more likely to be a simulated being inside a computation than a base-level being in the fundamental physical reality. You are probably, if the argument holds, living inside a simulation. This argument is not as easy to dismiss as it might initially appear, and several serious scientists and thinkers have engaged with it at length. Elon Musk has publicly stated that he believes the odds of us not being in a simulation are billions to one. Physicist Neil deGrasse Tyson has said that he thinks the argument is compelling enough to take seriously. Cosmologist Max Tegmark has written extensively about related ideas in his mathematical universe hypothesis, which proposes that mathematical structures do not just describe physical reality, but actually are physical reality, that every mathematically consistent structure exists as a physical universe, which would make the distinction between a simulated universe and a base-level universe philosophically murky at best. And some physicists have pointed out that certain features of our universe, like the fact that it appears to be digital at the Planck scale, the fact that it obeys precise mathematical laws, the fact that the speed of light acts like a maximum processing speed, and the uncertainty principle acts like a resolution limit, are at least consistent with the hypothesis that we are running on some kind of computational substrate. None of this is proof of anything. The simulation hypothesis remains a philosophical speculation, and there are strong counterarguments, including the fact that simulating a universe in sufficient detail to fool conscious observers might require computational resources comparable to an actual universe, making the whole exercise pointless, and the fact that we have no evidence whatsoever for the existence of the supposed simulators. But the hypothesis is not obviously false either, and the fact that it cannot be easily dismissed is itself philosophically significant. It forces us to confront what we mean by real, what we mean by physical, and what the relationship is between mathematical structure and physical existence. Questions that sit at the intersection of physics and philosophy, and that our current frameworks are not equipped to answer definitively. What connects all of these ideas? The hard problem of consciousness, panpsychism, integrated information theory, the simulation hypothesis, is a single underlying theme. The relationship between mind and universe is not as clear as we once assumed. For most of the history of science, the working assumption was that the universe is a purely physical place that exists independently of any observer, and that minds are a late, local, accidental product of physical evolution in one corner of that universe. But the more deeply we investigate both consciousness and the foundations of physics, the more that clean separation between observer and observed seems to dissolve. Quantum mechanics already tells us that the act of measurement, the act of observation, plays a fundamental role in determining the physical state of a system, a fact so strange and so resistant to intuitive explanation that physicists have been arguing about what it means for nearly a century without reaching consensus. Some interpretations of quantum mechanics, most notably the many worlds interpretation proposed by Hugh Everett in 1957, suggest that every quantum measurement causes the universe to literally branch into multiple parallel universes, one for each possible outcome, with a version of you in each branch experiencing a different result. Every moment. In this picture, the universe is endlessly forking, producing an ever-expanding multiverse of parallel realities, most of which we will never have any access to. Other interpretations, like Cubism, take a radically different approach and suggest that quantum states are not descriptions of objective reality at all, but are agents' beliefs about what they will experience when they make measurements. In this view, quantum mechanics is not a theory about what the universe is, but a theory about how rational agents should update their expectations based on their experiences. The universe, in this picture, does not have a definite state independent of observers. Reality is, in some deep sense, participatory. It is something that conscious observers help bring into being through the act of observation. We are far from understanding consciousness. We are far from knowing what the relationship between mind and physical reality truly is. But what we can say with confidence is that the universe, through 13.8 billion years of evolution, has produced at least one kind of system, the human brain, that is capable of reflecting on its own existence, of asking where it came from, of wondering what it is, and of being genuinely astonished by the scale and the strangeness of the reality it finds itself in. Whether consciousness is a rare cosmic accident or a fundamental feature of reality woven into the fabric of space-time itself, its existence changes something about the universe. A universe that contains beings who can contemplate it is different, in some meaningful sense, from one that cannot. We are not just inhabitants of the cosmos. We are the mechanism by which the cosmos has come to know itself. And in our final part, we will ask what that means for where we go from here, what the future of this cosmic self-awareness might look like, and what it would mean for humanity to carry that awareness forward into a future as vast and as strange as the universe itself. That is where part 10 will take us, and it is the most important part of all. We have come a long way together. We started in absolute nothing, before space, before time, before any physical thing existed at all, and we watched the universe explode into being from a point smaller than any measurement we can make. We watched the first stars ignite in 200 million years of darkness, watched their deaths scatter the building blocks of everything across the cosmos, watched gravity patiently assemble those scattered atoms into galaxies and solar systems and planets over billions of years. We watched life crawl out of the chemistry of a young ocean on a small rocky world orbiting an unremarkable star in one arm of one galaxy among 2 trillion. We sat with the unsettling silence of the Fermi paradox, wrestled with the incompatibility of our greatest theories, stared into the mystery of dark energy pulling the universe apart at an accelerating rate, and ended the last part staring into the deepest mystery of all, the fact that the universe somehow produced minds capable of asking what the universe is. And now we arrive at the final question. Not where did we come from, but where are we going? What is the future of this fragile, extraordinary, cosmically improbable thing called human civilization? And what role might we play in the long story of the universe that still stretches ahead of us across timescales that make all of human history look like a single frame in an infinitely long film? To answer that honestly, we have to start with where we actually are right now. And where we actually are is both more remarkable and more precarious than most people allow themselves to fully appreciate on any given Tuesday afternoon. We are, by any reasonable measure, the most technologically capable civilization that has ever existed on this planet, and quite possibly the most technologically capable civilization that has ever existed anywhere in the observable universe, though the Fermi paradox should make us humble about that claim. In the last 200 years, a period that amounts to less than 1/10,000th of 1% of the age of the universe, we have gone from horse-drawn carriages to spacecraft leaving the solar system, from candlelight to the ability to illuminate entire cities from a single power station, from communicating by letter carried across continents on foot to transmitting information to any point on the planet instantaneously at the speed of light. We have decoded the instructions that build a human body, split the atom, landed on the moon, built machines capable of beating the best human minds at chess and Go, and increasingly at scientific reasoning itself. The pace of our technological development is without precedent in the known history of life on Earth, and it is accelerating. But we are also, at this same moment, a civilization facing existential challenges of a scale and urgency that we have never encountered before, challenges that are themselves a product of the same technological capability that makes us so remarkable. Climate change is reshaping the biosphere that all life on Earth depends on, driven by the same industrialization that lifted billions of people out of poverty and built the modern world. Nuclear weapons, first developed in the same decade that saw the discovery of the expanding universe, remain pointed at each other in arsenals large enough to end human civilization many times over, held in check by a doctrine of mutual assured destruction that has worked so far, but that rests on the assumption of rational actors making rational decisions in moments of extreme crisis, an assumption that history gives us limited confidence in. Engineered pandemics, enabled by the same advances in biotechnology that are giving us new tools to fight cancer and genetic disease, represent a threat that grows more severe with each passing year as the technical barriers to creating dangerous pathogens continue to fall. And artificial intelligence, perhaps the most transformative technology humanity has ever developed, is advancing at a pace that is outrunning our ability to understand its implications, let alone our ability to govern its development wisely. The physicist Stephen Hawking said, in the years before his death, that he believed humanity needed to become a multi-planetary species within the next century or face a significant risk of extinction. Not because he was pessimistic about human ingenuity, but because he understood that concentrating all of human civilization on a single planet meant that any sufficiently large catastrophe, whether caused by our own technology or by a natural event like a large asteroid impact or a supervolcano eruption, could end everything in a single stroke. The universe has been running experiments in life for nearly 4 billion years on this planet, and 5 times in Earth's history, a mass extinction event has wiped out the majority of species alive at the time. The 6th mass extinction is happening right now, driven largely by human activity, and while humans themselves are not currently at risk of immediate extinction, the trend line of biodiversity loss, habitat destruction, and climate disruption is moving in directions that become increasingly difficult to reverse the longer they continue. Against this backdrop, the space programs of the world, and increasingly the commercial space ventures of private companies, take on a significance that goes beyond exploration or scientific discovery. They represent the first serious steps toward the most important insurance policy in the history of life on Earth: the distribution of the biosphere and human civilization across more than one world. Mars is the most discussed target, and for good reason. It is the most Earth-like planet in our solar system. It has a day length almost identical to Earth's. It has water ice at its poles and potentially in its subsurface. It has a thin atmosphere that could in principle be thickened over long timescales through a process called terraforming. And it is close enough that travel times, while long by human standards, are at least conceivable with existing rocket technology. SpaceX's Starship program, NASA's Artemis program returning humans to the moon as a stepping stone, the growing interest of multiple national space agencies in Mars exploration, all of these represent the early, tentative, enormously difficult first movements toward making humanity a multi-planetary species. But Mars, as extraordinary an achievement as getting there would be, is itself just a beginning. On the timescale of millions of years, if humanity survives and continues to develop technologically, the solar system opens up as a habitat in ways that are almost impossible to fully imagine from where we stand today. The asteroid belt contains enough raw material to construct habitats with a combined living area thousands of times greater than the surface of Earth. The outer planets and their moons offer environments of extraordinary diversity, each one a world unto itself, each one a potential home for some future form of human or post-human civilization. The physicist Freeman Dyson proposed in 1960 that a sufficiently advanced civilization might eventually dismantle a planet like Jupiter and use its material to construct a vast shell around its star, capturing all of the star's energy output. Such a structure, now called a Dyson sphere, would provide a civilization with energy resources so vast that our current entire global energy consumption would be to it what a single candle is to the sun. Whether such engineering projects are physically feasible remains debatable, but the point is that the resources available in a single solar system, if accessed with sufficiently advanced technology, are sufficient to support civilizations of almost incomprehensible scale and complexity. And beyond our solar system, the stars themselves. This is where the timescales stretch from millions to billions of years, and where the boundaries between science and speculation become genuinely blurry. but it is also where the most profound possibilities lie. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away, and it has a planet, Proxima Centauri b, orbiting in its habitable zone. At the fastest speeds achievable by our current best technology, reaching Proxima Centauri would take tens of thousands of years. But concepts for future propulsion systems, from nuclear pulse propulsion to laser-driven light sails to theoretical antimatter drives, suggest that travel times might eventually be reduced to decades or even years. The Breakthrough Starshot initiative, backed by serious scientists and substantial funding, is actively developing the technology to send tiny laser-propelled probes to Proxima Centauri within a generation, probes that would arrive in roughly 20 years and transmit data back to Earth. The first interstellar mission in human history may not be as far away as it seems. But interstellar travel is not just a technological challenge. It is a challenge to our conception of what humanity is and what it means to be human. A civilization spread across multiple star systems, with light years of distance between its constituent parts and communication delays of years or decades between them, would not be a civilization in any sense we currently understand. It would be something new, something without precedent in human experience or human thought. The different communities, developing in isolation over centuries or millennia, would inevitably diverge, biologically, culturally, technologically, philosophically, in ways that might eventually make them as different from each other as different species are today. The question of what connects them, what makes them all still in some sense human or descendants of humanity, and what obligations they have to each other across the vast distances of interstellar space, are questions that our current ethical and political frameworks are nowhere near equipped to address. And then there is the question of artificial intelligence, which may be the most immediate and the most consequential wildcard in any projection of humanity's future. We are currently living through the early stages of what many researchers believe will be the most transformative technological development in human history, the creation of machines with general reasoning capabilities that meet and then exceed those of the human beings who built them. The implications of this development, if it proceeds as many experts expect it to over the coming decades, are almost impossible to overstate. A machine intelligence significantly smarter than the smartest human being, with access to all of human knowledge and the ability to improve its own capabilities recursively, could in principle compress centuries of scientific and technological progress into years or even months. It could solve problems that have defeated humanity for generations, from aging and disease to the unification of physics to the discovery of life elsewhere in the cosmos. It could design the technologies needed for interstellar travel, crack the mysteries of dark energy, decode the hard problem of consciousness, and answer questions we have not yet thought to ask. But the same capability that makes artificial general intelligence so potentially transformative makes it potentially the most dangerous technology humanity has ever developed. A superintelligent system whose goals are not precisely and robustly aligned with human values and human flourishing could pursue those misaligned goals with a competence and a resourcefulness that makes human opposition futile, not out of malice, but simply because misaligned optimization is dangerous regardless of intent. The field of AI alignment research, devoted to ensuring that advanced AI systems reliably do what their developers intend, and that what their developers intend is genuinely good for humanity, is one of the most important scientific and engineering challenges of the current century, and it is receiving far less attention and resources than its importance warrants, given how rapidly the relevant technology is advancing. What all of this means, when you step back and take in the full picture, is that we are living in an extraordinary moment, not just in human history, but in the history of the universe. 13.8 billion years of cosmic evolution, from the Big Bang through the formation of stars and galaxies and solar systems, and the origin of life, and the long climb of evolution through single-celled organisms and multicellular life, and the Cambrian explosion and the age of dinosaurs, and 5 mass extinctions, and the emergence of primates, and the development of language and writing and science. All of it has arrived at this precise moment, when one species on one planet has developed the knowledge and the technology to either destroy itself or to carry the flame of awareness and intelligence forward into a future that stretches across billions of years and potentially across the entire galaxy. The universe did not intend this. The universe has no intentions. It operates by physics, not by purpose. The Big Bang did not happen in order to produce us. The stars did not explode in order to make carbon for our bodies. Evolution did not proceed in order to produce human consciousness. All of it happened through blind physical processes, gravity and chemistry and natural selection operating without foresight or goal. And yet here we are, aware, curious, capable, standing at a crossroads that no previous form of life on this planet has ever stood at. Looking back at 13.8 billion years of cosmic history and forward into a future whose length and richness depend entirely on the choices we make in the next few centuries. Carl Sagan said that we are a way for the cosmos to know itself. What he meant is that in us, the universe has produced something genuinely new, not just another form of life adapting to its environment, but a form of life capable of stepping back from its environment and asking what it is, where it came from, and where it is going. The universe was here for 13.8 billion years before anything could ask a question about it. And now something can. Now something does. And that something, fragile and flawed and magnificent and terrified and curious and brave, is us. The stars that burned and died billions of years before our solar system formed. The supernovae that scattered carbon and oxygen and iron across the galaxy. The long, improbable chain of chemical accidents that produced the first self-replicating molecule in a warm ocean 4 billion years ago. The hundreds of millions of generations of organisms that lived and died and were eaten and replaced and evolved over unimaginable time. Every step of that journey was necessary to produce this moment. You, watching this documentary, thinking these thoughts, feeling this sense of scale and wonder and smallness and significance all at once, are the universe's most improbable and most extraordinary achievement. Not because you are the center of anything, you are not. Not because the universe was made for you, it was not. But because in you, for the first time in 13.8 billion years, the universe opened its eyes. What you do with that, where you carry that awareness, whether you protect it or squander it, whether you extend it forward into a future as vast as the cosmos or allow it to flicker out on this one small world, that is not a question the universe can answer. That is the only question the universe has ever produced that you have to answer for yourself. The cosmos has done its part. It spent 13.8 billion years building you. The next 13.8 billion years are up to you. And on that note, this has been the universe, an unknown journey. Thank you for traveling with us, all the way from nothing to everything to here. You just traveled 13.8 billion years in one sitting. And if that felt like something, if somewhere in this video you felt that mix of smallness and wonder that reminds you why being alive is extraordinary, then do one thing right now. Hit that subscribe button, because next week we go even deeper, and you do not want to miss where we are going next. Share this video with one person, just one, who you think needs to be reminded how remarkable this universe actually is. And before you close this, drop a comment below telling me which part hit you the hardest. The Big Bang, the silence of the cosmos, dark energy, consciousness. Tell me. Because the conversation that happens in the comments of this channel is honestly just as important as the video itself. Thank you for watching all the way to the end. Most people do not. You did, and that says something about you. Now go look up at the sky tonight, even for just 1 minute, and remember what you are made of. We will see you in the next one.